Before we move on to a practical session on the microscope, let me just give you an overview of what is done when you are trying to obtain STEM images. As you can see, you would raster a probe and collect the signal here. So there are a few things that you need to do. The first thing is, when you go to the microscope and when you are operating in the STEM mode, you first switch to the STEM mode. When you switch to the STEM mode, you go to the micro probe or the nano probe mode. Depending on the manufacturer, there are different ways in which you do it. What happens when you go to the micro probe mode? You are actually fixing the potential of the objective lens, and there is hardly any influence of the objective lens on the image that is formed. Typically, the manufacturers such as Thermo Fisher, they measure it in terms of percentages. It is fixed at somewhat around 88% or something. It depends on the instrument configuration. The objective lens currents do not change anymore, and once it is done, you form a probe, and this is primarily using the condenser lenses, the combination of how many ever number of condenser lenses you have. In an ideal case, the perfect lens would form a very sharp probe like this, but in reality, because of various effects that I showed you earlier, you would form a probe which is definitely not converging at a single point. And as a consequence of this, if I think of how the point spread function of such a probe would look like, so this is like I take a Fourier transform of the probe, then in an ideal case it would appear like the sinc function with a very narrow peak, and this again, depending on the diffraction limit, your resolution or your probe diameter is limited, but this gets broadened due to the consequences of the aberrations that you have, and it appears like this. And if I take a projection of this, I can actually look at how the projection looks like. So in an ideal scenario, when this is impinging on my specimen, at the back focal plane or at the Fourier plane of this, I would see a disc kind of a pattern. So this formation of a disc now gives us some kind of a leverage in correcting for the aberrations of these lenses. This particular methodology of first correcting for small lens aberrations is actually called as correcting the Ronchigram in STEM mode. So when you switch to STEM mode, you should look at how the probe is formed. Based on the shape of the probe, you have to first bring the specimen to the right focus, bring it to the appropriate Z height. Once you bring it to the right height, go to an amorphous area in the specimen. Specifically, I am mentioning an amorphous area because when I collect this kind of an image or a Ronchigram from an amorphous area where there is no periodic arrangement of atoms, the image appears like this. Now, if I have corrected for my lens aberrations as much as possible within the available limits of the microscope, the Ronchigram or the image of the probe from an amorphous area in the specimen at the correct focus appears as a disc like this, and when I change the focus, the diameter of this changes. You can see that it appears somewhat like a dark spot with some kind of a circular ring kind of an appearance like this. In the practical demonstration videos, you would be seeing this. If my lens is aberrated, because I am looking at a projection, I do not know which component of the lens aberrations is contributing, but I will start seeing some kind of odd shapes like this. And the way I do change in the focus, so when I am changing the focus here, I would actually change the focus of the condenser lens but not the objective lens, because I have formed a probe here. So I go above and below the crossover point, I can see how the shape of this Ronchigram is going to change. and I have to try to make it as circular as possible, and even if I go over and under focus, if it remains nearly circular, I would have corrected my aberration due to the condenser astigmatism. And after this I have to insert an aperture. So let me give the aperture another color here. So let us say my aperture is somewhat like this. Depending on however small that this ronchogram appears, surrounding this I can place a physical aperture. The aperture here is typically the condenser aperture, and once I center this whole thing, correct for the ronchogram and place the appropriate condenser aperture, I am also fixing my convergence angle, and thereby my collection angles are also fixed depending on the camera length. I have to then go to a complete blank area or a hole, and I have to set my detector with background noise correction, bring the specimen in, look at how the signal appears like, and try to achieve the optimum contrast while I am imaging. So to cut this long story short, when I want to image in STEM mode, I have to switch to the STEM mode, do some corrections with the probe, and then insert the aperture. So this corrections of the probe involve condenser stigmatism correction, and then I have to insert the aperture, and then I start imaging while correcting the image contrast. This is if I am operating in a microscope which does not have an aberration corrector on the condenser lens. The aberration corrector on the condenser lens is called as a probe corrector, and there are some automated algorithms based on which this ronchogram correction is done. You have something called as the tableau. You actually apply a tilt, and based on the tilt, how my projection is changing, I can actually account for this, and I can correct for it, make it as symmetric as possible, and then I get nearly, I wouldn't say aberration free, but optimally aberration corrected images as well. So this is the area of STEM imaging, and it is a very powerful technique, and because I combine the positions of the probe at different regions on the specimen, and simultaneously I can also collect the EDS signal. For example, here is the EDS detector, or if I have an EELS detector, I can collect the EELS signal as well. It is a very powerful analytical imaging tool. So with this, I end our discussion on STEM. Now I'll show you how to image in STEM mode. The main difference between STEM mode and the other modes that you've seen here is previously you had the electron beam arranged like a cylinder, and you have an interaction of a parallel beam with the specimen. Here you are converging the beam to form a sharp point or a conical probe, and you raster through the sample, and you're collecting all the forward scattered signal that you have to form an image. How do we do this? To switch to the STEM mode, I go to this operation mode here and click on scanning, and you see there is some change that is happening. I get the image from the detector here. The detector is inserted in, and what is happening now is the probe is formed. Let me adjust the frame size here and the scan duration. Initially, for doing the alignments, let me stick to a smaller exposure time. I now have a 200 micron aperture inserted, and if I look at the live image here, here is how the detector looks like. So if I retract the detector, I'm essentially allowing the electron beam to form a probe, and I'm continuously rastering. It is now being rastered here. If I say scan stop and go to a spot mode, you see that there is the slight displacement of the beam here. This would stop right now. So as you can see, the image from the grid is here. I have to correct for the for the condenser stigmatism in STEM mode right here. So how do I do that? Let me show it on the CCD screen so that it is a bit more clearer for you. I can do the corrections here as well, but it is more handier doing it on the camera screen. As you can see here, this is from the grid area, and you see in the center of this particular region, there is some kind of an extension. So what is happening is, the image is now being formed by forming a conical probe and fixing it at a spot on the sample. And if I change the height now, so in STEM mode, one of the major differences is you're not imaging using the objective lens, but you're forming a probe using the condenser lens. So I have to correct for the condenser stigmatism. And even to correct for the condenser stigmatism, I need to go into an amorphous area and I have to bring the specimen to the correct height. I have done the eucentric adjustment of the sample for the objective lens. So there may be a difference in the height for the STEM mode versus the TEM mode. So if I now correct the height, as you can see, the magnification of the sample is going to increase, and at a condition where I have more or less this very high magnification and sort of circular shape that is formed, so this image you see here is because your beam is now stigmated. This is from an amorphous region. You only get this from an amorphous area from a sample. In a probe corrected instrument, you might actually go to a cross-grating sample and you'll correct there with a different principle, but it is always better to first go to such a region on an amorphous area and try to make it as circular as possible. So to obtain this image, you should have a trade-off between the correct camera length. You should be able to display this onto your CCD camera and tune the exposure time. Bear in mind that when you're focusing the beam to a cone, this is like you're imaging in the diffraction mode again. So keep the exposure times as low as possible. Here I've put it as 20 millisecond now. And I'll click the condenser lens stigmation button now. And I'll tune the stigmator to make it as circular as I can. So what you see here is actually called as a ronchogram. So in order to get a ronchogram, I have to go into the scan mode here, and please be sure that it is in a spot mode and not in a full area or an area scan mode. You do not see a ronchogram unless you are actually in the spot mode. And then I'm more or less at the right height. I've actually corrected for the focus, and as you can see, the minimal corrections I've done is forming a near circular shaped ronchogram. So this is more or less the right focus, closest to the right focus, and I have to correct the stigmation to make it as circular as possible. So just to help you identify this, let me draw a circular feature here. As you can see, it is as circular as I can. I can turn the focus here. So when I'm changing the focus in STEM mode, I'm actually not focusing with the help of the objective lens, but by changing with the condenser mini and the condenser lenses here, and I form an image. So once I correct for objective stigmatism like this, I go to the other screen, I'll form a STEM image here. So I've now made it as circular as possible, and to actually get a better STEM resolution, it is always advisable to use a smaller condenser aperture, and also see that the spot that you have here is centered with the detector that you're inserting into the path of the electron beam. So on this microscope, we have a HAADF detector, an annular dark field detector. So Firstly, I'll insert the aperture here. I'm putting in a 40 micron aperture. As you can see, the aperture is not centered, so I have to center it by moving it in this direction. The aperture is more or less centered. Now I insert the annular dark field detector. You would not see the shadow of the detector. So I'll just check if you can correct the gamma here. So you see the outer edge is the edge of the detector. So the most important thing is I have to remember to unclick the condenser stigmation knob after I've corrected for the stigmation, and I click on the PLA knob to see that the detector and the probe here are sort of centered. So once I've done this, I can lower the screen and I can start scanning from the area. So I'll switch to the other screen. So I can select the scan time here. I can click on the focus or search here, and let me start imaging. So what you see here is a STEM image from the gold cross grating sample. Now as you can see, the brightness and the contrast are not appropriate. So I can check the histogram page here, and I'll try to adjust this by making it as bright as I can. Typically, when I see a histogram like this, please remember there is one option of going to this auto location here and click on auto gain and offset. This is one way in which you get some kind of information. But typically, you see the histogram, the slope that you see here, this is somewhat of kind of a good condition or a reasonably good contrast. It varies from sample to sample, it varies from person to person, it depends on how you are actually going to present the image. So now one important aspect is obtaining the correct focus. So here I have the gold nanoparticles, and if I zoom in, because I corrected the height precisely while I was adjusting the stigmation or the condenser stigmation, I'm more or less at the right focus here. But let me see what happens if I change the focus. So you can select focus either by clicking on this and going to a small area where the exposure time is more. So I just turn the image focus knob. Or I can do it just in the live search mode. So once you're sure that you've gotten a good focus, what you can do is get an image from this area by choosing the scan setting. So I go to the record option here. I'm recording a 1024 by 1024 pixel image for a dwell time of approximately 30 microsecond per pixel, and let us see how this image is recorded. So from the top left to the right, the raster has started and it is actually obtaining a STEM image. You can in principle record series of images like this. You can record movies. You'll also get high resolution STEM images. Right now it is with probe size 6, so I have to correct it with probe size 8 or 9 to get high resolution STEM image. I intentionally stuck to probe size 6 because I want to show EDS mapping. In order to record EDS maps, you have to go to this software. This particular instrument has the Geol EDS detector. So you go to the SDD operation panel. It shows that the detector is now retracted. I have to insert the detector. Depending on your microscope configuration, you might want to tilt your specimen or orient your specimen into a particular angle, because to improve the collection efficiency of an EDS detector, it is advisable that your geometric parameters are considered, and most commonly you have to tilt the specimen along the alpha or the x direction to approximately 10 to 15 degrees to ensure you have a very good count. But in the modern microscopes where you have sort of segmented EDS detectors or the annular EDS detectors, you really need not tilt the sample. Now once I tilt the specimen to the right orientation, and I correct for the focus, what I can do is I import the image into the EDS software. I just click on the image button here, and as you can see, I get an image from the grid. And depending on the counts you have, the counts right now are approximately 1590 to 1700 counts per second, which is not too bad but not really ideal as well. But this is a gold thin film sample. Let us see what kind of a map we get. So in order to do mapping, I can go here, select the conditions that I want. Let us say, for a quick example, I'll do a short 128 by 128 pixel map, and I set the dwell time as 10 milliseconds, and let us try to get a map from the whole area. Let me choose the elements here. I will only show carbon from the grid, and let us select gold as well. You can actually do an auto quantification also, but nonetheless, let us see what you get here once I start mapping. So if I click on the map button, this window pops out, and it starts forming the image. To obtain the STEM images, we were previously using an aperture size of 40 microns. In order to obtain a good EDS signal, I switched to the 100 micron aperture, centered the aperture again, and as you can see, the counts are pretty prominent now, and the scan is going on here, and this is how you actually obtain an EDS map. It varies from a case to case, from a different specimen to another specimen. There are multiple factors that you need to be careful of. One is the takeoff angle, the kind of detectors you have, the collection efficiency, the thickness of the specimen, the spot size, the apertures if you're using the right combination. You should have enough signal such that you get meaningful information from the sample, but also you shouldn't cause a damage to the specimen. So it is a trade-off among multiple factors in order to ensure you get a good EDS map. The mapping from this particular area is nearly complete. As you can see in the background, there are some intensity profiles from gold and copper. The image on the left, gold and carbon, I'm very sorry. So image on the left shows you carbon, and this is from gold. Let me just do a quick quantification, and so on quantification, as you can see, the pink colored map here is carbon and the yellow one is gold. More or less all across the area you see some yellow spots, and all over you see carbon. But bear in mind that this is only a 128 cross 128 pixel quick scan. So when you're doing STEM imaging and when you're obtaining EDS maps, please bear in mind that there are multiple factors. What I've shown you is already an instrument which is quite stable and in more or less aligned condition. While you're starting with imaging in STEM mode, the first thing that you should ensure is your probe is actually well corrected. What I mean by probe is well corrected, I have to go to the alignment mode. On a Thermo Fisher instrument, I have to correct for the rotation center and ensure that the pivot points are aligned and so on. And on the J-hole microscope, I go to the alignment mode and see that I see a near circular shaped region from where I'm getting the ronchogram. And in order to get the ronchogram, please ensure that I'm not scanning the beam. I'm in a stationary mode and go to an amorphous area. And from the amorphous area, please ensure that your ronchogram is well corrected. Once you've done this, and you have to also ensure that the aperture is well aligned and the forward scattered signal that you're getting is centered with the detector. Do not rely on any of the auto brightness or contrast. They would work in most of the cases, but more often than not, it is better if you have an idea on how to adjust your histogram for your image as well. And once you have all this, you can start imaging and getting spectral maps as well. If you have an EELS detector, in the same way, by getting a signal from EELS detector, you can get EELS compositional maps as well. But right now, we only have the EDS compositional maps here. And in order to get a good quantification, you should see that your signal is good. Ensure that the detector is actually capable of collecting signal from the specimen at that particular orientation. Sometimes you might be interested in one particular crystallographic orientation, and the angle of the holder at that particular orientation might be completely off, and your collection efficiency might not be very good. In modern day microscopes where you have annular EDS detectors, this may not be a big problem. So all these factors actually play a key role in getting meaningful data from your STEM images.